we've derived iterative least squares. And now we do what we always do. Let's go ahead and implement it. So let's see here. I'm going to generate some synthetic data that fits the line model. We could have done this with a parabola too, but let's keep it simple. So here are my random parameters of a line. There's just 2 parameters. Notice here I'm generating a random number, 2 of them. I'm subtracting 3 and multiplying by 6 just to give me a range of values. I'm going to take a uniform range of x coordinates between -1 and 1, and then I'm going to evaluate y according to the model u0, u1, slope and intercept. And I won't add any noise here because it doesn't really matter for this particular iterative least squares. Here's my quadratic form. I need 2 things. I need the A matrix and the B vector. The A matrix is, let me define big X. Big X, of course, has X in the first column, X1, X2, up to Xn, and 1 in the second column. That's the standard X matrix from our least squares formulation. The A matrix is X transpose times X, and the B vector is X transpose times Y. Okay, why do I need those? Because the direction is going to use both of these quantities. All right, now let's do the steepest descent or the iterative least squares. Let me pick a random value u. And so here I'm just picking some random value between -5 and 5 for each of the coordinates. And I want to hold on to these estimates of u. Why? Well, I'm doing an iterative estimation. And so I never said when to stop. I said to stop when you hit the minimum. But how do you know when you hit the minimum? That is, after all, what we're searching for. And so when we stop is when 2 successive estimates of our model parameters, m and b, u0, u1, are very, very close together within a threshold, and then we just say we're at the minimum. So I'm going to hold on to the previous value so I can compare it to the next value. I've got this open-ended loop while true, because I don't know how many iterations, so I'm going to do an open-ended loop. I'm going to compute the direction, the residual as we called it also, which is just b minus a times the current estimate of u. I'm going to compute the step, which is the product of the residuals divided by the residual times the A matrix times the residual. And then I'm going to create the new estimate of u. So u sub j is equal to u sub I, the previous estimate, plus alpha times the direction ri. So there is just the 3 steps that you need. Pick a random point, compute the residual, compute the step size, and then increment. I'm going to append that to a big list called U, because I'm eventually going to want to plot these so I can see how I'm moving through my contour space. And then I'm going to ask if the difference between the current estimate of U and the previous estimate of U is less than some threshold. Here it's arbitrary. I picked 10 to the minus 3, so 1 over 1,000. Then go ahead and break out of the loop. Otherwise, update the previous value u sub I with the current value uj, and then do it over again. And so every step will be exactly the same. Pick the direction in the maximal descent, that's this down here, compute the step size, update, repeat, repeat, repeat until 2 successive iterations are very, very close. A couple things on the visualization. I like to visualize all the pieces. So I want to be able to visualize the contour plot. I want to be able to visualize where I started and what the steps were to get down to the minimum so I can see if I've actually hit the minimum in terms of the contour plot. This little bit of code here, which I won't go through, but you can look through yourself, is computing the error surface. Now, obviously, when you go to implement this in the real world, you wouldn't do this because it's incredibly costly. You can see I'm basically for a range of possible values of the 2 unknowns, I'm evaluating the error, which I wouldn't normally want to do because it's too expensive, but I'm just doing this for the purposes of visualization. And then I'm going to just plot everything here. So all of this is just a little bit of visualization. And then when I do that, I get something like this, which looks a lot like everything we've been seeing before. I've got my contours of equal error, which I've plotted. I've got my initial condition up here, and this is my initial direction, and there's the step size, and then I go again, I go again, I go again, and then you can't sort of see what's going on. Notice that these are perpendicular. That's exactly what we said they should be, every single one of them. And notice that I'm also getting what appears to be the minimum or very, very close within 10 to the minus 3 of the minimum. I've been interchanging the terminology here. We started off by calling this iterative least squares, and then I switched over to steepest descent. Those are synonymous. Those are exactly the same thing. And the reason we call this iterative least squares is because we're solving a least squares problem, but we're solving it iteratively. And the reason why we call it steepest descent is because at this point, I'm going down the steepest part of the error surface, steepest part of the error surface, steepest part of the error surface. So iterative least squares and steepest descent are synonymous. All right, now there's a couple of variants of steepest descent that we're going to talk about next. And what I'm going to do is I'm not going to derive them in the full detail because they tend to be, they're even a little bit more gory than what we just did. But they're really important to understand even if we don't see all the derivations, because in practice, you're going to have to pick between these different types of iterative techniques. And I'm going to enumerate a few more of them when we come back.